So today we start with chapter 3, shift register. Okay. So before we go forward, we go through the learning outcome. Okay, after learning this chapter, students should be able to identify the basic form of data movement in shift register. Okay, so shift register the basic component is flip-flops. So because flip-flop have a function of to storage data and move data, so you have to know how the basic form of data movement in shift register that contribute by flip-flops. Okay, a number of flip-flops lah. And then explain how serial in, serial out, or we can in short form is SISO, serial in, parallel out, SIPO, parallel in, serial out, PISO, and parallel in, parallel out, PIPO, shift register operate. Okay, and then determine how bidirectional shift register operates. Okay, after you know all the 4 types of shift register, so we will analyze some types of shift register. One of them is bidirectional, and we will analyze the output waveform for general shift register, and also ICs of register such as 74HC195. Okay, and then after that, shift register also have counters. Still remember counters? So shift register also have counters. They have 2 types of counters. So you can construct Johnson and ring counters from shift register. Okay, 2 types. And then describe shift register applications such as time delay, serial to parallel converter, UART, and keyboard encoder. Okay, so this is the learning outcome that I hope that you will understand after finish this chapter. Okay, so we go to first slide for introduction. Okay, register one or more flip-flop used to store or hold data. Okay, so that is the meaning, the keyword meaning for register. Okay, one or more flip-flop. So we know that the basic component is flip-flops to build a register. Okay, for shift register, a group of flip-flop used to shift or transfer data from flip-flop to flip-flop. Okay, that's why we call this register as shift register. Okay, so register can store data. Okay, and then shift register, we can move the data from one flip-flop to another. Okay, and then a group of D flip-flop connected in a chain, and the clock of the flip-flop is connected in a synchronized manner. Okay, so all the flip-flop for shift register is connected in the clock is connected in synchronized. Okay, not asynchronized, because asynchronous is a ripple, so we use synchronous manner. And then they are generally provided with a clear or reset connection, so that they can be set or reset as required. That's why during first chapter subtopic flip-flop, you have to know all of the component or function in one flip-flop. Okay, you have to know what function of clear, what types of flip-flop, for example D flip-flop, and so on. So this is the application, so you have to understand that. And then shift register available in IC form or can be constructed from discrete flip-flop. Okay, so actually shift register that have 4 types already built in one IC. Okay, IC chip too. Okay, and then in simple word, shift register has 2 basic functions. The first is data storage, second is data movement. So you have to remember this lah. Okay, data storage, data movement. And then type of shift register, that 4 types: SISO, SIPO, PISO, and PIPO. Okay, and then shift register have 2 functions: data storage and data movement. So you have to know after this slide, you have to know how this data storage function and how data movement function for shift register. Okay, so you have to understand this basic function of the shift register. Okay, firstly is data storage. Okay, so data storage, the storage capacity is the total number of bits of digital data it can retain. The total number of bits depends on the number of flip-flop being used. Okay, so the number of bits still depends on the number of flip-flop. Okay, storage capability make it important type of memory device. Okay, for example, okay, this example use one flip-flop only. Okay, for example, we have one D flip-flop. Okay, so when one is applied to the D flip-flop, okay, this one, input one, its output becomes 1 and the triggering each clock. Okay, so we have one input 1 in flip-flop 0, okay, FF0. For D flip-flop 0, we have input 1, this one, and then during first clock, okay, so you have to look at this type of clock. So this clock means positive edge clock. Okay, so during first positive edge clock, so this input 1 will become output. Okay, and then the output remains 1 until next trigger. Okay, so this one is still here, still remain here until for example, they have another flip-flop, and then when come with next clock, so this one will move to another flip-flop. Okay, therefore one is stored. Therefore this one during this function, okay, so we call as this one is the data one is stored. Okay, next, when 0 is applied to the D flip-flop, okay, if they have another input, for example 0, so its output becomes 0 at the triggering edge clock. Okay, so this 0 will be output here, so it will replace the input 1 from previous clock. Okay, the output remains 0 until next trigger, therefore 0 is stored. Okay, so that is how we call as a data storage. Okay, when flip-flop receive input at a triggering clock, and then that input will still remain in that flip-flop, in that particular flip-flop, so we call as that data is stored or data storage by flip-flops. Okay, next is data movement. Okay, shift capability permits data movement within the register or into or out of the register when triggering by clock pulse. Okay, so for example, various data movement of 4-bit register, 4-bit register with direction indicated by arrow. Okay, so this is flip-flop. Okay, so for flip-flop, 1, 2, 3, 4 flip-flop, meaning that 4-bit register. Okay, 4-bit register. So this is a data in. Okay, and then data in serially, and the data is out serially also. So we call this type as serial in, serial out, or SISO. Okay, so this is SISO. All right, and then so this SISO is in from left to right direction, and this one from right to left direction. Still same type, SISO, just different direction. Okay, and then this is the data in serially, and the data out will out parallelly. So we call this shift register is serial in parallel out, or SIPO. Okay, SIPO. And then this is data in parallelly. Okay, the data is in parallelly, and the data will go out in serial. So this type is parallel in, serial out. So this is piezo. Parallel in, serial out. Okay. And then another one is parallel in and parallel data out. Okay. So parallel data in and parallel data out. So we call this shift register type as PPO. Okay. Parallel in, parallel out. Okay. So this is another data movement. Okay, not type of shift register. Okay, just how the data movement. So actually, the shift register can rotate the data in right direction or in left direction. Okay, so this is the data movement. Okay, so today we will cover one type of shift register, which is CISO. Okay, so CISO shift register. Okay, the serial in, serial out shift register accept data serially. Okay, that is 1 bit at a time on a single line. Okay, serial mean the data is in 1 bit per time or 1 bit per clock. Okay, and then the serial out means 1 bit also will out per clock. Okay, it produces the store information on its output also in serial form. Okay, so output serial, input serial. So accept data serially. So this is CISO. Okay, the IC, if you find IC model 74HC1965, so this IC can be CISO shift register. Or we can use 74HC195, that is universal for shift register. Okay, 74HC195 can be any type of shift register. So this IC can be CISO and can be another type. Okay, so each clock pulse will move an input bit to the next flip-flop. Okay, so figure 1 shows 5-bit CISO shift register. Okay, so we have 1, 2, 3, 4, and 5 flip-flop. So meaning that we have 5-bit CISO shift register. Okay, so the number of bit, just count the number of flip-flops. So if they have 5 flip-flop, meaning that we have 5-bit shift register. And then you have to make sure how the data input insert into this shift register. If the data in serial, so this is SI, and measure the data output if in serial, so meaning that the shift register is serial in, serial out. Okay, so the full name for this shift register is 5-bit serial in, serial out shift register. Okay, so example, 5-bit serial in, serial out shift register. So each clock pulse will move an input bit to the next flip-flop. For example, a 1 is shown in as it moves across. Okay, so first we have data 1, and during first clock, so this data 1 will move to here. Okay, and then next clock, this data 1, second clock will be here, third clock will be here, fourth clock will be here, and fifth clock will be here. Okay, so this shift register should have 5 clock. Okay, 5 clock to move the first data to be output. Okay, this example is only for one bit data only. Baru satu data saja input. Okay. Okay, we look into in details. Okay, to shift 101 starting with LSB. Okay, so this is 3-bit CISO shift register. Okay, the data that we have to analyze, move is 101. Okay, So to shift this 101, we start with LSB. So which one LSB? So this one is the LSB. Okay. So initially all flip-flop are being reset. So for sure, as usually we will assume this shift register initially reset, meaning that Q2, Q1, and Q0 is 000. Okay, initially. Okay, and then at first clock, shift register contain 001. Okay, so this is how we write the data. We start with MSB. Okay, MSB on the leftmost the most left is MSB, which is Q2, and until LSB. Okay, this one is for our writing. So we did that, but in shift register, we start with LSB data input. Okay, so this data one will be here. Okay, so during first clock, clock 1, so this data bit 1 will move to be here. Okay, that is first clock. The output for FF1 and FF2 still remain 0 because initially the data is 0. Okay. Okay, but this 0 is actually come from the previous 0. Okay, and then this 0 also come from the previous 0. Okay. Okay, second clock shift register contain 0, 1, 0. Okay, so bit 0 second data is here. Okay, for clock second. Okay, so clock second bit 0, so this bit 0 become here, and this one will shift here. Okay, next for second clock. Okay, and then this 0 will be here. Okay, so this is what happened during second clock. Okay, so the shift register contain 0, 1, 0. So third clock, which is bit 1, we move to here. Okay, so third clock, the shift register contain 101. All 3 bit input have been completely stored. Okay, so third clock, this bit 1 and it become output here, and this 0 is come from here. Okay, and this one come from here. So during third clock, so all 3 bit input, which is 101, already stored in every flip-flop in this 3 bit shift register. Okay, so during third clock, all input already stored. Okay. Okay, what happened after that? So during fourth clock, okay, the first bit is shift out. Shift register contains 0, 1, 0. Okay, now we just move 101 data only. We have 101 bit input. After that, we assume they have no data, meaning that 0. Okay, so after third clock, all 101 is already stored, and then for fourth clock, no data, so we assume the data that insert into first flip-flop during first clock is 0. Okay, so this 0 will be here. This one come from the previous, this one. Okay, this one is become output 1 at FF1, and this 0 come from output FF1 previous clock. Okay, so this 0 become here. Okay, so the register contains 0, 1, 0. So next, fifth clock, the second bit is shift out. Okay, so this is the second bit already shift out. Okay, during fifth clock. Okay, first clock, the first bit is shift out, which is input 1. Okay, bit 1. Second bit shift out during first clock is input 0. Okay, this one. So at this time, the shift register contain 1, 1, 0, 0. Okay, and 6 clock, the third bit is shift out, which is 1. Okay, this third bit is shift out. Okay, so for 6 clock, the register is clear, already been clear. Okay, right. So this is the example of how the data movement for 3-bit input, which is 101, for 3-bit shift register CISO. Okay, this is the table and the waveform. Okay, shifting 3-bit code into the shift register. So initially 0. So this is the first flip-flop, second flip-flop, and third flip-flop. Okay, this one, FF0, FF1, FF2, Q0, Q1, and Q2. But I write in table form. Okay, in truth table. So initial condition clock, this is clock. So initial clock, all flip-flop is 0. And at first clock, input 1, so we have input 1, 0, 1. So this LSB become output for Q0. And then this one become here, shift here. Okay. And then second clock, this input will be here, this one will be here, shift here, this 0 will shift here. Okay, and then third clock, this input 1 move here, and this 0 shift here, and this one shift here. Okay, so all 3-bit 101 input already stored. Okay, 101 already stored in all 3 flip-flops. Okay, after that, we want to shift out the input. Input 101, we want to shift out. So start with fourth clock. Okay, so initially 101 is here lah. Okay, actually clock 3. Okay, so during first clock, the first bit input. Okay, this is the first bit input. Okay, that come from here, and come from here, and come from here. Okay, so this is the first bit input. So this bit is shift out during fourth clock. Okay, so during first clock, this one is shift out. Okay, shift out. Okay, and then this 0 shift here, and this one shift here. This 0 come from, we assume nothing happen, or we doesn't have another data to input, so we assume f is 0 data. Okay, okay, so for, and then fifth clock, this 0 is shift out. Okay, so this one come from here, this 0 come from here, and this 0 is assume 0. 6 clock, we assume 0, and this 0 shift here, this 0 shift here, and this one shift out. Okay, so all data 1, 0, 1 will already shift 1, 0, 1. Okay, so already shift. So this is the data in 101 input data, and this is the output that shift out serially. Okay, serially mean 1 bit per 1 bit. Okay, so that is for in table form, and this is for waveform. Okay, timing waveform. So we have this is the clock. So during first clock we have input 1. Say okay, this input 1, this one. So the Q node will, because this is D flip flop, so D flip flop first clock when receive input 1, so it will be 1 for 1 clock cycle. Okay, this is, we assume 0, initially 0. Okay, so first clock Q node will be 1 for 1 full cycle. Okay, this is 1 cycle. Okay, so this is a positive edge or rising edge. Okay, so Q1 will be 0 because of shift from initial condition 0, and this 0 also come from initial condition 0. Okay, next second clock, the second data is 0, this one 0. So the 0 Q node will be 0 for 1 clock cycle, and then for Q1 it will be 1 because it shift from here. This is 0 come from this one. Okay, and then third clock we have data input 1, this one data input 1. So clock Q0 will be 1 because this is D flip flop. Okay, and then this 0 is come from here, and this one is shift from here. Okay, so this is 1, this is 0. Okay, so during third clock, so the data bit store after 3 clock. So this is in waveform, timing waveform. So we also can see that during third clock, all the data, 3-bit data 101 is already stored inside each flip flop. Each flip flop Q0, flip flop for Q1, and flip flop for FF2 or Q2. Okay, and then after that, start with clock 4. So the data will start shift out. Okay, during first clock, so we assume the data is 0. Okay, start with clock 4. So Q0 will be 0. Q1 will be 1 because of shift from previous flip flop, which is Q0. And then this 0 is come from Q1. Okay, 0. Okay, so this data, first bit data 1 already shift out. Okay, so shift out. Okay, and then fifth clock 0, so Q0 will be 0. Q1 will be 0 from shift from here. Q2 will be 1 shift from here. So this bit 0. Okay, second bit tadi dia pergi kat sini. So this input 0 already shift out. Okay, during 6 clock Q0 will be 0. Q1 will be 0 also from here. Q2 will be 0 also from here, and the first bit, the last bit, okay, this is the last bit 1, then shift from here to here and to here. So this one's already will be shift out. Okay, so during so during 6 clock, the data bits are clear after 6 clock, and all 3-bit data input is already shift out. Okay, this is shift out. This is the data that contained inside the flip flop, that we assume that this shift register is already been clear. 0, 0, 0. Okay, this is timing waveform in large scale. Okay, so meaning that we have 3-bit CISO shift register. So meaning that we require 3 clock. Okay, 3 clock for a store to store all 3-bit data. Okay, to store 3 data bit store after 3 clock pass. Okay, because this is 3-bit CISO, so we have 3 data input, 3-bit data input. So we required 3 clock to store all 3-bit data, and also another 3 clock to shift out and the data. Okay, and also another these three clock to clear the shift register. Okay, so this is to shift out data. Because this is CISO, serial in, serial out, so the data is out serially, 1 bit per 1 bit. Okay, so that's why we need 3 clock. Okay, because this is 3-bit CISO shift register. Okay, understand? What we can conclude here, for 3-bit CISO shift register, we need 3 clock to store and another 3 clock to shift out data. Okay, how about 4-bit CISO shift register? So how many clock required to store and how many clock required to shift out the data, the 4-bit data input? So this is the answer. Okay, 4-bit CISO. Okay, for example, 101. So 4 clock required to store. Okay, to store data. And after 8 clock pass, the data is already shift out. This is store. This is shift out. Okay, so we need another 4 clock for shift out all the 4-bit data and also clear the flip-flop. Okay, so meaning that for 3-bit we require 3 clock to store and 6 clock, total 6 clock to shift out data. For 4-bit we required 8 clock to shift out data or clear the shift register. For 5-bit CISO, we required 10 clock paths to shift out the 5-bit data and also to clear the shift register. Okay, simply like that lah. So you just times 2. Okay, so you can see this is how the 4-bit data store. Okay, this first input during first clock and second clock, sorry, this one. Okay, third clock and fourth clock here. So this one shift from to here, and this one to here, this one to here, and this is here. Okay, this is what actually happened. Okay, so first clock, all 4-bit data input is already being stored. Okay, 101. Okay, store for first clock and start with 5th clock. This 1 bit per 1 bit will shift out. So this one will shift out. Okay, so this one will be here, 0 will be here, and this one will be here. So this one we assume 0 or clear. Okay, and then 6 clock, 7 clock, and 8 clock. So during 8 clock, the register is clear, or all 4-bit data is already being shift. 1, 1, 0, 1. Okay, so this one from 5th clock, this is 6 clock, 7 clock, and this is 8 clock shift out. Okay, So in timing waveform or timing diagram for same data input 1011 and same shift register for bit ISO, so it will be like this for first 4 clock, and the next 4 clock will be like this to clear the shift register. Okay, understand? Okay, so you can do this exercise. So we will discuss next week. We will next class start from this slide. Okay.